Hello class. Today I have a beaker of hot water, a pop bottle, and what I'm going to do is I'm going to pour a little bit of hot water into this bottle. I'm going to stopper the bottle, and we're going to give it a little shake here. Well, that went pretty far. Right on, so why did that happen? Why is it that when I gave it a little shake, that rubber stopper went flying? So that stopper launching from the bottle shows the relationship between pressure and temperature. Now, what is this relationship? Well, the person who discovered this relationship is Gay Lussac, and he did this while taking balloon flights. Many scientists at the time were fascinated with hot air balloons. And he actually held a record that was held for a very long time. He took a balloon to a height of 7,000 meters. And on his balloon flights, he would again sample pressure, temperature, humidity. And from this, he was able to establish a relationship between pressure and temperature. So what did he find? Well, he found that pressure and temperature are directly related. Right? If you have a confined gas and you heat it up, the pressure as a result is going to increase. If you have a confined gas and you cool it down, the pressure as a result is going to decrease. Right? As you heat up something, what happens to the kinetic energy of those gas particles? Well, they're going to be moving faster, right? They're going to hit the sides of your container more often, and as a result, that pressure is going to go up. Now, we saw that in the pop bottle experiment, right? When I shook that pop bottle, what was I doing? Well, I was exposing that hot water to the air, heating up the air, the pressure went up, and as a result, that stopper shot out. Now, the Kelvin scale which we explored yesterday was actually determined, that absolute 0 point was actually determined using Gay-Lussac's data. And what did this data look like? Well, unshockingly, it looks very similar to volume and temperature, because volume and temperature, again, are directly proportional to one another. But what he did is he took his data, Lord Kelvin that is, and then he traced that down to our x-axis, and again found that that temperature at which there theoretically would be no pressure, right, because there's no movement of your particles, is at negative 273.15 degrees Celsius, or 0 Kelvin. So again, these two things, pressure and temperature, just like volume and temperature, are directly proportional. So if we double our pressure, what do you think is going to happen to our temperature? Our Kelvin temperature will also double. If we half our temperature, what's going to happen to our pressure? Well, our pressure will also be cut in half, right? So one change in pressure will result in an equal change to your temperature. So what are some practical applications of Gay-Lussac's law, this relationship between pressure and temperature? Well, some of you have your driver's licenses at this point, and you may have noticed that as the spring hit, what happened to the pressure in your tires? Right, as we went from minus 40 degrees Celsius to now plus 10-ish, what happened? Well, you should have noticed, especially if you have those TPMS sensors in your vehicle, that your tire pressure increased. Well, why did it increase? Well, it increased because the temperature increased. On the flip side, in the winter, I often need to add air to my tires. Why? Why in the winter would I need to add extra air to my tires? Well, that's because it got very cold, and as a result, my tire pressure went down. Another practical application of this is looking at any confined gas canister. So whether it's hairsprays, propane canisters, all of them have that little Wimmis symbol on the side for pressurized gas. And they say you should not expose to flame, to heat. Why? Well, as you heat it up, that container, what's going to happen to the gas inside? It's it's going to get excited, it's going to hit the sides of your container more often, pressure is going to increase, and eventually that container is going to fail. It's going to explode catastrophically. So you have to be very careful of this when you're working with pressurized gases. All right, so let's look now at a couple example problems on how to solve pressure and temperature relationship problems. Okay, so if a 12-liter sample of gas is found to have a pressure of 101.3 kilopascals at 0 degrees Celsius, calculate the new pressure at 128 degrees Celsius if the volume is held constant. So we are going to use the exact same steps we have been using. So we are going to predict, and then we are going to multiply by the ratio that fits our prediction. So first, let's write down what we have. So we know that our initial pressure is 101.3 kilopascals, right, which is 1 atmosphere of pressure. We know that our temperature is initially 0 degrees Celsius, and we know that our final temperature is 128 degrees Celsius, and we are looking for our pressure. What is our new pressure as a result in the change of our temperatures here, in the change in our temperatures? So what did we do? We went from 0 degrees to 128 degrees. So we've increased our temperature. And since pressure and temperature are what? They are directly proportional. That means that our pressure should also increase. Now, just like working with volume temperature relationships, we have to use an absolute temperature scale. We cannot use Celsius, right? From 0 to 128 degrees Celsius, what happened? Did we double our temperature? Did we go up by 1.5? Did we triple our temperature? We don't know until we convert that into Kelvin. So how do we do that again? Well, we have to add 273.15. So if we add 273.15, we add 273.15, we find that our temperatures in Kelvin are 273.15 Kelvin, and that is going to be 401.15 Kelvin. So what did we do? Did we double our temperature? Did we not quite double our temperature? If we would have doubled our temperature, it would be like 546-ish, right? So it's not quite double. So you should expect your answer to be less than double. So what ratio am I going to multiply by? Am I going to multiply by 401.15 over 273.15, or am I going to multiply by 273 over 401? Well, remember our prediction. Our prediction was that if our temperature increases, our pressure, therefore, must also increase. So we are going to multiply by 401 over 273. So we have 101.3 kilopascals, and we're going to multiply this by 401.15 over 273.15, and this gives us approximately 149 kilopascals. Okay, second example. If a gas at 20 degrees Celsius and 1 atmosphere of pressure is found to have a pressure of 40 kilopascals after cooling, what temperature is it cooled to in degrees Celsius? Now, whenever you're given pressures, whether it's in Boyle's law or Lussacs law, it is important that those pressures match and are the same when you're doing your calculations. So you have to convert them. So remember, you always will have to convert to make sure your units are the same, whether that's in temperature or pressure or volume. So how do I convert here to make my units of pressure the same? Well, we know that 1 atmosphere is equal to 101.3 kilopascals. Now, how then will I convert 1 atmosphere to kilopascals or 40 kilopascals to 1 atmosphere? Well, you just have to multiply by a ratio, and that ratio here is going to be your conversion factor. So let's convert 1 atmosphere to kilopascals. Now, this is nice and easy because it is 1 atmosphere. We know that 1 atmosphere is equal to 101.3. But if it was any other value, you would use this same strategy. And what's the strategy? Well, you want to make sure your units cancel out. So we'll put, for every 1 atmosphere, there are 101.3 kilopascals. And our atmospheres here, they cancel out because we have numerator, denominator. And what are we left with? We're left with kilopascals. So whenever you do any conversion, whether it's a stoichiometric conversion or a conversion of pressures or temperatures, you do want to use a ratio to do so. So we know that 1 atmosphere is 101.3 kilopascals. So what are the initial and final conditions, right? We want to still do that same prediction. So initially, we know that our temperature is 20 degrees Celsius. And we know that our initial pressure is 101.3 kilopascals. We know that our final temperature is what we are looking for, and our final pressure is 40 kilopascals. Now, what do we do to our pressure? We decreased our pressure, therefore what's going to happen to our temperature? Our temperature should have also decreased. And I did give that away in the question with the word cooling and cooled. So what is our prediction? Our pressure decreased, and since they are directly proportional, our temperature must have also decreased. Okay, so how then do I solve for our new temperature? Well, can I take 20 degrees Celsius and multiply it by the ratio of my pressures? No, I can't. Why not? Why not? Well, again, our temperature has to be in Kelvin, right? So how do I convert this to Kelvin? Well, I add 273.15 to get our temperature in Kelvin of 293.15. Okay, so our temperature is going to go down. Now, what am I going to multiply my temperature by? Well, that's going to be the ratio of my pressures. Am I going to do 40 over 101 or 101 over 40? We want it to go down, so we're going to do 40 over 101. So if I do 40 over 101, I get, that should be about 115.76 Kelvin. Now, 115.76 Kelvin, what is that in degrees Celsius? Because that's what I'm asking for, right? I'm asking for degrees Celsius. So this is going to be subtracting 273.15 to give us, that's going to be minus 157.39 degrees Celsius. So again, very common mistake here. Students will often forget to convert their temperature to Kelvin, and they will also often forget to convert their pressures such that the units are the same. Remember, your units here, they want to cancel out. If they don't, you're going to get the question wrong. Right on. Have a good day, everyone.